Welcome back. You should aim to master how to use the standard normal distribution table for calculating probabilities of less than and also for greater than, as this skill will come in very handy as we move toward chapters 7 to 11. We will also be doing several exercises on Friday to become completely familiar with how to use the standard normal table. We can do it the other way. Suppose the manager of the store wants the probability of a stock out to be no more than 5%, i.e. to be less than 5%. He can then determine what the reorder point should be. Hint, given a probability, we can use the standard normal table in an inverse fashion to find the corresponding z-value. Graphically, this is it. We want to find the z such that the probability that there will be a stock out, i.e. the probability that demand will be greater than whatever that critical x is, will be no more than 5%. So, what do you think should be the procedure? Since we know the area to the right, we also know the area to the left. It must be 0.95. Hence, we then turn to the standard normal table to find what that z is that is consistent with the area to the left being 0.95. There is no easy way to do this. You'll just have to plunge your fingers into the table and look for the number closest to 0.95. The number that's closest to 0.95 is approximately 1.645. Something like that. No, 1.645. So keep that number in mind because that's going to be the critical z. Since 1.645 is the critical z, we can then just use the equation for converting z and invert it. And as you will see from the gray box, this gives us 24.87 or approximately 25 gallons. Hence, if the store manager sets the reorder point at 25 gallons, there will be only a 5% chance that there will be a stock out during lead time. Graphically, this is the picture. You can check for yourself that value for x of 24.87 is consistent with only a 5% stock out probability. And this is also just another description of the situation we have solved. Now, remember chapter 5 where it was mentioned that the normal approximation can be used to solve probabilities of binomial random variables. When the number of trials n becomes large, then calculating the probability becomes too cumbersome. In that case, we can use the normal approximation. But please take note, it's important that two criteria are fulfilled, and these are the ones highlighted in red, i.e. NP should be greater than or equal to 5, and n times 1 minus p should be greater than or equal to 5. These two must be fulfilled before you can use the normal approximation. If these two criteria are fulfilled, then all you do is calculate the mean of the binomial variable as being equal to n times p, and its standard deviation as being equal to the square root of np times 1 minus p. Once you have those two values, you can then convert the binomial number, whatever it is, into a standard normal and then use the table. But here's another important procedure. You have to add and subtract a continuity correction factor, because remember, the binomial is a discrete random variable, whereas normal is continuous. So for instance, if you're trying to compute the probability x equals 12, what you have to do is compute the probability of x being greater than 11.5 and being less than 12.5 if it were continuous. The adjustment of 0.5 to the right and to the left will be okay for most circumstances. So let's try an example. Suppose that a company has errors in 10% of its invoices, and a sample of 100 invoices has been taken, i.e. n equals 100, and we want to compute the probability that 12 invoices contain errors. To reiterate, n equals 100, p equals 0.1. Are the two criteria fulfilled for using the normal approximation? Please take a minute to find out for yourself. Yes, the two criteria are fulfilled. So in that case, the next step is to calculate mu and the standard deviation. And they are just 10 and 3 respectively. And graphically, this is what we're trying to do. We're trying to calculate the area between 11.5 and 12.5. So how do we do that? First, we have to convert x into standard normal form so that we can use the table. But please also note that this is also how we would decompose that area. Let's go back. It's the area in green. Now note that that area in green is just equal to the area to the left of 12.5 minus the area to the left of 11.5. And what's left is the thin sliver in between. Let us now look at the exponential probability distribution. It can be used to describe time between arrivals at the toll booth, time required to complete a questionnaire, etc. Which discrete probability distribution does the exponential distribution sounds like? The answer will be in slide 52. A property is that its mean and standard deviation are equal, and it is skewed to the right. And this is its density function. So all you need to do is you want to find out the probability of x being a certain number or less, then you just plug in its value into this formula. Here is an example. Arrivals follow an exponential probability distribution with a mean of 3. Now Al wants to know the probability that the time between two successive arrivals will be 2 minutes or less. This is just the graphical illustration. And if you plug in 2 into the cumulative probability function, you will get 0.4866, i.e. there's a 48.66% chance that the arrival time will be 2 minutes or less. Now, please test your understanding of the exponential function by computing the probability that the arrival time will be between 1 and 2 minutes. Finally, as some of you may recall, the exponential distribution sounds very much like the Poisson distribution, which we discussed in Chapter 5.